Mr. Pelton. This is Algebra 2, Chapter 6, Section 3. This is the Part 4 on the graphing of logs. So what it comes down to with graphing of logs is the base itself. Okay. So the base itself tells you whether it's growth or decay. If that base is greater than 1, you have growth. If that base is between 0 and 1, you have a decay problem. You can't be 1, obviously, because it wouldn't be growing or decaying. And you can't be negative. It's not possible. Okay, the domain and range does not change in either one of these cases. You'll have a vertical asymptote at 0 unless there's some kind of translation, and the base point will pass through 0 unless there's a translation or some kind of transformation. And obviously, the inverse is the exponential function. So if you see down below, I've given them some basic examples from prior sections to here. So the first half of the chapter is exponentials. So if you look at the log graph, it is the inverse of the exponential function. They're both growth because you read left to right. They're both going up. And the log graph is the inverse of the exponential function. You read them left to right. They're both decay. They're both going down. And they're inverses because they're both symmetrical on the y equals x line. Meaning if you switch the x and y values, you'll get the other one. So one undoes the other. So let's do some basic graphing of logarithms. Okay. So in the first example here, we're going to do a log base 2. But you don't really want to graph logs as is. So this is the equation format of a log. We're going to convert that to an exponent. So that's 2 to the y equals x. If I go, right? Convert that down to there. So you think about it. Do you want to plug in x? Do you want to plug in y? Which one's easier? If I plug in x and I plug in a 5, 2 to what power is 5? I don't know. 2 to what power is 5? I don't know. Okay, so I don't want to plug in x, I want to plug in y. That's a lot easier task. Okay, so you're kind of working backwards from what we did with exponents. So 2 to the negative 2 is 1/4, 2 to the negative 1 is 1/2, anything to the 0 power is 1, and of course these are 2 and 4. So at 1/4 we're at negative 2, at 1/2 we're at negative 1, 1, at 2 we're at 1, and at 4, 1, 2, 3, 4, we're at 2. So we get a graph that's like this. Okay, and we get an asymptote at x equals 0 is our asymptote. That is the line that you can't cross. Okay, so intercepts. X-intercept by definition, y is 0. Y-intercept by definition, x is 0. Because if you're on the axes, the other values must be 0. So if I plug in 0 for y, I get 1 for x, don't I? Well, that's a point we already have in the table. But if you plug in 0 for x, that doesn't work out so nice. Let's try that. 2 to the y equals 0. Well, 2 to what power gives you 0? Positive numbers? Negative numbers? 0? No, it's not possible. But look at the graph. There's also an asymptote there. You can't have a y-intercept. Vertical asymptote, x equals 0. We already figured that out because essentially the table goes 1/2, 1/4. If you keep going, what does it do? 1/8, 1/16, 1/32nd, 1/64th. It's getting closer and closer and closer to 0, but you never get there. Horizontal asymptote, there isn't one. Okay, because it's going forever in both directions. You're not really worried about that. It's going up and down forever. So it's crossing over. So domain, it's trying to get to 0. It can't get there. So that's the least it can be. So we use a parenthesis, not a bracket, and it goes to infinity. Range, it goes forever up and forever down. So there is no restriction there. Okay. All right, let's go to the next page and try another example. Oh, and that was growth because you read it left to right, it goes up. So this one is base 1/2. So this will be a decay problem. So this is really y equals log base 1/2 of x, but we don't want to write it in exponent format. So that's 1/2 to the y equals x. Again, you don't want to plug in x, you want to plug in y. It's a lot easier. So this is 1/2 to the -2, which is 2 over 1 squared, which is simply just 4. So 1/2 to the -1 is 2. Anything to the 0 power is 1, 1/2, and 1/4, right? Okay, so at 4 we're at -2. 1, 2, 3, 4, we're at -2. At 2 we're at -1. At 1 we're at 0. Half we're at 1. And a quarter we're at 2. So we have the decay graph of the log. And again, we have an asymptote at x equals 0 as our asymptote. That is a vertical asymptote. Okay. And of course, it's going 1/2, 1/4, 1/8, 1/16. Can never get to 0, hence why that's there. There is no horizontal one. The asymptotes, if you're an x-intercept, by definition, y is 0. If you're a y-intercept, by definition, x is 0. If I plug in 0 for y, you get 1. If I plug in 0 for x, it's not possible. 1/2 to y, no matter what y is, you cannot get 0. But we already knew 1, 0 was a point anyways. It's in our table. So our domain is 0 to infinity because I can't get any negative x's in there. But my range is forever up and forever down. Okay, pause the video, try the student problems. Okay, first problem. This is really y equals log base 3 to the x, or in exponent format, 3 to the y equals x. Okay, so we'll plug in y values. So 3 to the -2 is 1/9. That's 1/3, 1, 3, and 9, right? Okay, so if I graph those at 1/9, I'm at -2. At 1/3, I'm at -1, 1, 0, 3, 1, and 9, 2. We got x equals 0 asymptote, which is a vertical one. There is no horizontal for logs. Okay, and you can see this goes 1/3, 1/9, 1/27, 1/81st, right? You're never going to get to 0. So the domain is 0 to infinity for the x if you look at the x table. But the range goes forever up and forever down because I can plug in anything I want for y. So the intercepts by definition, y is 0 and x is 0. Y is 0 for an x-intercept, and x is 0 for a y-intercept. You can look at any graph, pick any x-intercept you want, and that is true. So if I plug in 0 for the y, I get a 1 for the x. However, if I plug in a 0 for x, there is no exponent that will give me a 0 outcome. That is not possible. Okay, and that is a growth function because the base number is 3. And clearly left to right, it is growing. If you read the graph left to right. Let's try the last one. Okay, 1/3 is a decay problem because clearly the base is between 0 and 1. So this is log base 1/3 of x using the y equals. So we'll change it to a exponent format. So that's 1/3 to the y equals x. So we'll plug in y's because that's a lot easier. So 1/3 to the -2 is 3 over 1 to the 2, or 9 over 1, or just 9. Next one gives us 3, 1, 1/3, and 1/9. You can do that one if you want. Okay, so at 9, I'm at -2. At 3, I'm at -1. At 1, I'm at 0. 1/3, I'm at 1. And 1/9, I'm at 2. You can clearly see if I didn't miss the points. Left to right, this is decay, which is what we thought because it's a 1/3. There is still a vertical asymptote at x equals 0, the invisible line I can't cross. That's why it's dotted. So that's x equals 0. There are no horizontal asymptotes, not applicable for horizontal. X-intercepts, if I plug in 0, 1/3 of the 0 is 1. And if I plug in 0 for x, it's not possible to get a 0 outcome. 1/3 to no power, yes, that's not possible. Okay, 1/3, there's no y that'll give me 0. Not possible. So domain, I can go to 0, but not get there and go infinitely. So my y value, my x values in the table and graph. And my y values go forever up and forever down. I can pick anything you want. That is the end of part 4.